With that, it's my pleasure to introduce today's speakers, Mark Longman and Barbara Luneau. They will be presenting on revisiting the Upper Cretaceous Niobrara Petroleum System in the Rocky Mountain region. Mark received his BA from Albion College in 1972, followed by a PhD in geology from UT Austin. He joined the research lab of City Services in Tulsa for 5 years before moving to Denver in 1981 to work for Coastal Oil as an exploration geologist in the Williston Basin. From 84 to 2006, he was a consulting geologist before joining QEP, where he worked as their rock expert until 2018. Mark specializes in the description of cores, cuttings, and petrographic thin sections, with a focus on integrating sedimentology and petrology with reservoir studies and petrophysics. He has worked extensively on Cretaceous rocks and reservoirs in the Rocky Mountain region, and on Paleozoic rocks in the Williston and Permian basins. Mark has published more than 40 papers in journals ranging from RMAG's The Mountain Geologist to the AAPG Bulletin, and in 2014 co-edited AAPG Memoir 107 on the Pinedale Field. In 2016, Mark received AAPG's Distinguished Service Award, and currently Mark is a research associate at the Denver Museum of Nature and Science, an affiliate faculty member at Colorado School of Mines, and a part-time consulting geologist. Barbara Luneau received her bachelor's degree in geology from the University of Vermont in 1981, followed by a master's degree from UT Austin in 1984. She worked with RPI International from 85 to 91 in stratigraphic studies teams studying the Gulf Coast, Mid-Continent, and Rockies. From 92 to 2017, Barbara worked as a consulting geologist in reservoir characterization and modeling, first with Intera and then with Schlumberger. She is currently an independent consulting geologist specializing in data integration, and 3D reservoir modeling. And like I mentioned, Barbara will be helping to facilitate the question and answer section at the end of the lecture. So please, we would love your feedback. We welcome questions. And so with that, please welcome Mark Longman and Barbara Luneau. Thank you.
Thank you, Dan. It's an interesting experience for me to be here trying to talk to 100 and some odd people sitting in the comfort of my desk chair with socks on. But that's a good start, I suppose. So if this is working, hopefully you can see the slide, my title slide, with a picture of the Lyons Quarry up near Lyons, Colorado, also called the Cemex Quarry. And this picture was taken about 1991, so I'm sure that rock face doesn't exist anymore. But you can see at the bottom part of that quarry behind the pickup truck, layered rock that's the Fort Hays member, and above that, the marls of the Niobrara Formation. And I have to say, I do like studying carbonate rocks, and that's how I got involved in studying the Niobrara way back in 1990 for a study that RPI was doing with a number of different clients. And we went to this quarry and looked at the rocks, and my first impression was, boy, these are ugly rocks. These are just not much fun. They're dark, they're nearly black, and they're layered, and just, I would call them boring. So what I'd like to do now that I'm starting this talk is just to introduce you to the two terms that I'm going to use over and over again through this session. The first term is chalk, and it refers to the more calcareous or carbonate-rich beds in the Niobrara. Some people call them chalk benches, and they're often lighter colored. And the other term I'm going to use is marl, and most of what you're seeing above the Fort Hays in this picture is the marl. They're relatively dark gray, almost black. Sometimes they get a little bit of gypsum or calcite precipitated on them, so they look white in parts of this photo. But we're going to be contrasting chalks and marls for the next 35 or 40 minutes in the Niobrara Formation and talking about how they form and what they mean. So just to give you another clue how you distinguish chalks and marls, there's a gamma ray log in the upper left corner of this photo taken from a handheld scintillometer by Roger Slatt and his students in the Lyons Quarry. And you can see a black band of relatively organic rich marl that has a higher gamma ray response relative to some of the other chalks. So a gamma ray is a really good tool for helping distinguish chalks versus marl. So I'm going to set some background here to try to make sure we're all on the same page. And I thought I'd do this with just an introduction to the Niobrara and a question. Why has the Niobrara received so much attention over the last 50 years, actually going back to Earl Kaufman and his students in the 60s and a number of other people? For one, it has scattered good outcrops, and outcrops are always fun if you like to look at rocks. It has common cores. Now we have a lot of continuous cores through the whole Niobrara Formation. Those are really useful. And then for Earl Kaufman and others that like the Niobrara, it's full of fossils, mostly forams, some ammonites, some other things like coccolus. It contains a lot of calcium carbonate, so that's why we have quarries like that Lyons quarry. It has common type 2 marine organic matter, which is a source for oil and gas, and therefore it's not surprising the Niobrara has a lot of oil and gas. And it has common bentonites, which help us age date it and correlate and so on. So those are all good things. A lot of people like it. It's got something for everybody, including me, maybe including you. So I have two goals in this presentation. I really want to start the talk by looking back at what we did in 1998 when we published a paper. Barbara Luneau, my co-speaker today, and Susan Landon, and I put a paper in the Mountain Geologist I'll tell you a little bit more about shortly. So I want to see what we've learned in the last 20 plus years, and then I want to review and revisit the Niobrara depositional processes. I think that we've learned a lot about Niobrara deposition that I didn't know in 1998. So here's an outline of my talk, very simple. We're going to go through that 1998 study, get in our time machine and go back 20 plus years and see what we thought was going on, what we used as data, what we knew. And then we're going to take that as a starting point and see what has been done on the Niobrara since 1998. A whole lot has happened in the last 22 years. We're going to look a lot at the controls on chalk versus marl deposition in the Niobrara. And everybody knows there are chalk benches that are good reservoir zones and marls that are less good quality reservoir zones. And we want to see what's controlling that deposition. The traditional interpretation is that sea level changes, transgressions and regressions, controlled whether you got a chalk or a marl during the time of deposition. We'll revisit that. A little more recently, in 2008, Locklear and Sageman put a paper together that said a lot of Niobrara deposition is controlled by Milankovitch climate cycles. And they recognized three different types of cycles. Well, Milankovitch himself recognized the three different cycles. Precession's a 23,000 year sequence cycle, obliquity 41,000 years, and eccentricity with 100 to 400,000 years. I want to focus especially on eccentricity. It's one that I understand very little, but you're going to see that a lot of deposition in the Niobrara does reflect cycles of 100 to 200, even 300,000 years. So we'll look a little more closely at that later. I personally really like to think about flow patterns in the Western Interior Seaway, the currents, whether they were flowing from north to south and they carried cold water across the Colorado region, or whether they were flowing south to north and carried warmer water. And we'll look at regional trends and then especially look at some characteristics of the interfingering of chalks versus marls. And then lastly, and this was very eye-opening to me, a paper came out in 2018 that dealt with a recent analog off the South Island of New Zealand. And it just opened my eyes to all sorts of things that might be going on in water depths that are fairly significant, much greater than the Niobrara deposition. And then we'll look at some conclusions. The paper I keep referring to is this Longman, Luneau, and Landon paper in the Mountain Geologist in 1998. Still available, still a useful reference, commonly cited. So I'm proud of that piece of work, but there are a lot of things I would improve if I were to redo it. And that's why we're revisiting the Niobrara today. Our database for that 1998 paper consisted of over 1,000 wells that we correlated all through the area from New Mexico, northern New Mexico, all the way up to the Canadian border. We put together regional cross sections. We were able to find 47 cores, mostly at the U.S. Geological Survey. We described facies. We made a bunch of thin sections, 100 thin sections or more. Ran Rocky Val and TOC on another 100 samples. Defined stratigraphic markers. We generated facies maps. We looked at burial history. And we really felt like we developed a regional context here that was unusual in its scope, covering parts of 7 states and hundreds, more than 10,000 square miles. One of the cross sections we generated goes from west to east across southern Wyoming into Nebraska, just for letters, it's CC prime. And you can see how we were able to define the chalk benches in the Niobrara. We used different terminology for our first study. We used an alphanumeric code, so A100 was the A chalk, and N100 was the A chalk, and N400 was the B chalk, and so on. But we've adopted terminology that's commonly used in industry. We just call them the A chalk, the B chalk, and the C chalk, and they're separated by marls, the A marl, the B marl, and so on. I think terminology is pretty easy here. And I'd like to call your attention to the B chalk. A lot of people think the B chalk is just a single massive chunky chalk, and that's not true at all. There's a marl in the middle of it that correlates just beautifully across a lot of the area. So we're going to divide the B chalk into an upper B chalk and a lower B chalk separated by a B marl. And our conclusion was that these chalk benches could be correlated because they were relatively blanket-like deposits, and they behaved as we expected they should on our model for deep marine deposition. But they thinned. The chalks thinned westward and pinched out as the marls thickened over in western Colorado and on into Utah. So I'll revisit that model that we were using in just a moment. Let me show you a couple more slides. One of the slides that I used and we published in that paper to summarize the depositional trends was this commonly seen diagram. I think it's second only to Earl Kaufman's regional cross-section of the Niobrara that he published in 1977, stuck in the lower right corner of the slide. But our slide used arrows to indicate clay content increasing northward, temperature of the waters increasing southward, and then water depth and clays and sand being shed off the severe highlands being obviously highest to the west, TOC content, and calcium carbonate content increasing southeastward into the incipient Gulf of Mexico. Again, this was published in our 1998 paper. And I, since then, have had two people really say, Mark, you made two mistakes on that diagram. And it's always a little bit embarrassing when they're caught. And you say, well, yeah, I'm sorry. So if you're really smart, you'll already know what these two mistakes are. The first one is in the water depth columns, which shows an almost symmetrical western interior seaway. Both arrows are pointing more or less toward the middle. Clearly that's wrong. The deepest part of the seaway was along the western margin. We know that. Earl Kaufman showed that in 1977. So if I could redo this slide, I would change the arrows for the depth and make sure that they showed the asymmetry of the western interior seaway, much more gradual ramp on the east, steeper dips into deep water on the west. The second error that we made, or that I made, I should take it personally, was the TOC content. And I had a nice big arrow increasing in TOC content pointing eastward because all the rock data that we had from cores and so on showed TOC increasing toward eastern and northeastern Colorado, up to 4 and 5, even 6% in some of those marls. And what we didn't do is get any source rock data, TOC data in Kansas or Nebraska on the eastern side of the basin. And it turns out TOC drops fairly quickly as you move east across Kansas and Nebraska. So in this figure that you're looking at now, I've added a second arrow that's westward pointing toward a high that's somewhere in northeastern Colorado or southeastern Wyoming. And that was not on the original figure, but it certainly should have been. So we get smarter as we go. The traditional idea for Niobrara that's been espoused by Kaufman going back into the 1960s was that the Niobrara was a cyclothem. The greenhorn's another cyclothem. They represent maximum times of transgression. And within those cyclothems, as Kaufman called them, there were several transgressions and regressions. He actually numbered these. There's the N7 transgression and the N7 regression and on and on. And we took a log from Wattenberg Field and just tried to put these transgressions and regressions using Kaufman's model of deeper water for the chalks and shallower water for the marls. And it was all very obvious that you could start to see high stands and low stands during Niobrara time. And I've taken this one step farther. I've tried to go to various sources of the literature and put absolute ages for the top and bottom of the different chalk units in the whole Niobrara. And we start to see some interesting things. For starters, the whole Niobrara represents about 6.6 million years of time. The whole Cretaceous period represents 79 million years of time. So to put this in context, that 6.6 million years is far less than 10% of the whole Cretaceous. And yet I think the Niobrara has received about 50 or 70% of the publications on the Cretaceous. So that little thin section of rock is actually way overrepresented in the literature. Even more profound to me is if you try to date the chalks, and if you ignore the A chalk, because in Wattenberg the A chalk goes all squirrely and thins and gets truncated and there's some other things going on. You can see the A marl has a duration of roughly 500,000 years, 83.9 to 84.4 million years. So that's not bad, 500,000 years. The B chalk, which is about as thick as the A marl, represents 200,000 years. The B marl represents about 200,000 years. The B2 chalk is 200,000 years. Wow, this goes with the eccentricity of the Milankovitch cycles. And yet the B marl is quite a bit thinner than the chalks. And that just tells you that maybe when the chalk factory, the carbonate factory for the chalks got cranking, it could produce quite a bit of carbonate in a short time. The B2 marl then is 600,000 years, and there's some other ages down there. The C marl is unusually long, over 1 million years. But it gives something to think about in terms of the duration of what these different intervals were doing. And I think I'll leave it at that. We'll see this slide again shortly. So I tried to put in words what we knew, what Barbara Luneau and Susan and I knew as we did the Niobrara study and published it in 1998. And I thought, well, I think I'm speaking for a lot of people. So I used the title on this slide, some things almost everyone knew in 1998. The Niobrara was a deep water deposit, and I put deep water in quotes. I don't know what people think. I think around 100 meters, maybe 200 meters maximum. Certainly wasn't 1,000 meters in my mind. But deep water environments were quiet and boring with slow passive deposition. I just had this idea not much happened in deep water because I didn't have any way to get down into deep water and check out what was happening. Siliciclastic sediment transport to form the marls. Siliciclastics and the marls, are the clays and the silts, was transported dominantly easterly from the severe highlands to the west. So, yeah, no surprise, the Niobrara pinches out as you go westward. Siliciclastic sediments dominate. That all makes perfect sense. Chalks themselves, the chalk benches, formed from a gravity-driven rain of pelagic debris, coccoliths, forems, copepod, fecal pellets, and so on, and were blanket-like deposits. That's why we could correlate them over tens or even hundreds of miles. So simple gravity-driven rain of carbonate forming up in the upper part of the water column, settling to the bottom. And then once sediment was on the deep sea floor, it was stable. It didn't move much. Maybe it didn't move at all. Maybe it got some burrowers, and that was about the extent of it. So our model for Niobrara deposition is summarized in these 4 points. A very simple, quiet rain of carbonates at certain times, interbedded with marls at other times. Then I tried to take those words and create a picture, because I think in pictures, and I'm not a very good artist, so you'll have to bear with me here. But I wanted to try to summarize the key points for low stand deposits, which are in the top slide, when you had marls deposited, versus high stands when you had chalk benches deposited in the lower slide. And then the first question I had to answer, I'll step back. This is a cross-section representing as much as 650 miles. It starts way out in eastern Utah, it goes across Colorado into Kansas. And of course, we don't really know what's going on in eastern Kansas because the Niobrara and the Cretaceous is all eroded off over there. But let me use eastern Colorado as a starting point. We think the water depth in eastern Colorado, maybe during a low stand, was 200 feet. I don't know, maybe it's 300 feet, maybe it was 100 feet. It was below wave base. There's not much going on in those rocks. So it's just a guess. How about 200 feet of water during a low stand? And then in contrast, if you go to a high stand, how deep was the water? Well, I'm going to make an estimate. I'm going to say it's 100 meters or 300 feet. And you got to think now, we're looking at 85 million years ago in the upper Cretaceous. The climates were warm. There were no glaciers. We cannot have glacial fluctuations in the upper Cretaceous like we did in the Pleistocene, where waters would change by hundreds of feet just as the glaciers receded and melted and so on. So I'm going to say the maximum change in water depth in Niobrara time was maybe 100 feet, maybe even that's high. So then when it's low, can you envision all these siliciclastic deposits coming in from the west, from the severe orogenic belt, flooding out across the seaway all the way to eastern Colorado, maybe another minor influx from eastern Kansas somewhere, and creating these marls that you can correlate for miles? I've added 2 terms to this slide. Hypopycnal flows are those low density, fresher water plumes of sediment coming off rivers that can move out tens or even hundreds of miles into a basin, and hyperpycnal flows. Those terms were not used in 1998, but they provide a mechanism, a process for transporting all these siliciclastics out into the seaway. In contrast now, in a high stand, Kaufman and others would imply that water depth went up. Let's say it went up by 100 feet. I don't really know. That was enough to reduce the influx of mud. And instead of muds and marls being deposited, we got pelagic carbonates raining down on the seafloor, forming these chalk benches up to 90, 95% chalk, and so little siliciclastic. And I'm thinking to myself, the severe orogenic highlands probably had many hundreds of feet of relief. There might have been a broad coastal plain of a few miles or tens of miles, but changing sea level by 100 feet doesn't remove the severe highlands. They're still shedding debris. There's still rivers and so on coming in. So I thought, the more I thought about Kaufman's model and this high stand, low stand that's been our gospel for years, the less I liked it. It just doesn't fit with what I think is going on. And I would welcome comments after this talk is over if I'm missing a key point here. But I'm going to leave it at that now. And I'm going to try to say, if it's eustatic sea level that's controlling chalk versus marl deposition, we should be able to go to the edges of the basin and correlate the Niobrara with deposits that show high stands and low stands. I can't do that very well in Kansas because the shoreline over there has been eroded, but I can go westward into Utah. And very fortunately, Lauren Bergenheyer back in 2017 in sedimentology put together the stratigraphic column for eastern Utah, and she had absolute ages as best she could determine. And I realize there's some slop in these numbers. There's slop in the numbers for the Niobrara too. But if you just take that red box for the whole Niobrara and superimpose it on her diagram, which is on the right side of this, and then you mark where the B chalk and the C chalk and A chalks are. A chalk, again, is a little bit odd because it's representing a lot more time than the thinness in the Wattenberg field would imply. You can see that there's not much of a correlation. The B chalk equivalent, the biggest chalk in the Denver Basin, correlates with the Emery sandstone plus or minus, and that's not a high stand sandstone. That's a prograding sand that's coming out into the seaway. And the A chalk is probably the worst of all. You've got that whole prograding Blackhawk sequence with all those different members, and clearly no evidence in Utah where Lauren was working of that major transgressive event that other people have said corresponds to the A chalk. So I'm going to call this a disconnect. I'm going to say I don't understand it completely, but I don't see evidence in Utah in the stratigraphic column as proposed by Lauren Bergenheyer and her ages that the same high stands and low stands worked over there. So another possibility, which occurred to Susan and Barbara and I as we were doing our work back in 1990 and 91 and published in 1998, was that maybe current flow directions in the Western Seaway were important. And I'm going to play a little game with a pun here. This idea got little traction back when we published it because the idea was unorthodox. And even worse, we just didn't have good modern analogs to show the same thing. So here we are, going to show you some diagrams that I thought beautifully captured regional trends in the Niobrara. These were put together during a brainstorming session with Alan Scott, a professor of mine, and Barbara's back at the University of Texas many years ago. And Alan is quite the artist. We could sit down and we could tell, well, we think we have this rock here and we have that rock there, and could you create a block diagram and show all these things? So this is the block diagram that we ended up coming up with, thanks to Al's artistic skills, for the Fort Hayes, the basal part of the Niobrara. And a couple interesting things. We thought there might be a big delta coming in from the West Sevier Highlands, all those black arrows on the left side. If you looked at the Fort Hayes, where the limestone is well developed, it's shaded blue with that brick pattern. And a puzzle came to our minds. In South Dakota, you've got a beautiful Fort Hayes section, and you move across the state line into northeastern Wyoming and specifically into the Powder River Basin, and there's no Fort Hayes. And yet you're at the same more or less latitude. You would think that the same processes forming the Fort Hayes in South Dakota would have been working in northeastern Wyoming, but they're not. There is no Fort Hayes, which raises the question, why not? Well, we could partly answer that with these arrows on the diagram suggesting that cold Arctic currents were following the deepest part of the seaway, flowing southward and bringing in waters that were not conducive to forming the carbonate organisms, forams and chalks and so on, in Wyoming in the Powder River Basin. But in South Dakota, we had warmer Gulfian currents coming up from the Gulf of Mexico on that very broad, flat eastern shelf of the seaway, carrying those warm carbonate-rich waters all the way north, up as far as North Dakota. So this was our first attempt to explain how water currents, ocean currents, northward flowing on the west, deeper part of the seaway, caused marls or non-calcareous Fort Hayes deposition from the Fort Hayes in South Dakota. So that's the starting point. We went on and tried to do a similar diagram for the B chalk. Again, the B chalk, as everybody knows, is the biggest, thickest reservoir interval in the Niobrara across much of the Denver Basin. And we saw this as a time when you had dominantly northward flowing warm Gulfian currents carrying warm waters all the way up across the Powder River Basin, all the way up into Montana and North Dakota. In Canada, this grades into the white specks. And in contrast, we had the Arctic currents that are colder and denser, just crawling along the western margin of the seaway, the deepest part over there in westernmost Colorado into Utah, and preventing the carbonate-producing organisms being deposited there. If you look really closely at this diagram, you'll see little blue, dark blue pods. The purest chalks are the darkest blue. And we recognized even back then there were thicks and thins in the B chalk, and we didn't really know how to explain it. But I'm going to come back and look at those little thin areas of blue in a later slide just keep in mind, we recognize those in the beach hawk. They're a very important part of the reservoir story. And in contrast, we had the sea marl shown in this diagram, which has some of the most organic rich source rocks in the Niobrara. When this slide was put together back in the 1990s, if you wanted to answer the question of where are the best hydrocarbon source rocks in the Niobrara, you'd look at the sea marl. A marl is pretty good too. And TOC gets up over 6 to 8%, and that's pretty good. I'm going to show you that we've learned more about these organic rich source rocks, and there are actually more organic rich beds in the Niobrara that we missed in our initial study, but that's a subject later. We think that the marls formed when you had colder Arctic currents flowing southward and preventing the carbonate producing organisms from getting very far up into the basin. We even go a step farther. You've got the Hartville uplift labeled HU in the Los Animas Arch, LAA, creating a starved basin with laminated black shales or marls in the highest TOC and extend across northeastern Colorado into western Nebraska and so on. So just part of the story, and I still like this part of the story. I think it does help explain why we have those organic rich marls in areas interfingering with the chalk benches. And much to my pleasure, when I started researching a revisit to this Niobrara, I came across a 2018 paper published by Chris Lowry and 8 others in Earth Science Reviews. And my goodness, doesn't this look neat? He's got the same warm, saline, oxygen-poor, carbonate-rich waters coming up from the Gulf of Mexico. He called them Tethyan waters, and cool, brackish waters. And I'm thinking to myself, well, 20 years after our 1998 paper, someone's catching on, but better late than never. Just one of those things. We do quibble with a few details in here. I'm not going to go into that right now. So enough of looking back at our 1998 paper. What have we learned in 22 years since then? I think we've learned a lot. So the Niobrara has become a primary focus of exploration and horizontal drilling in much of the Rocky Mountain region. Quality of the Niobrara hydrocarbon source rocks is recognized. When we started our study, most people would have told you the Mowry was the best source rock for oil in the Rocky Mountain region. We proved that the Niobrara is significantly better than the Mowry in terms of total TOC content and lateral distribution and some other factors. So that was a key part of our work and other people's work in the last 20 years. Hundreds of Niobrara wells, horizontal wells have been drilled in Colorado, Wyoming, to a lesser extent New Mexico. That's pretty amazing. Just all that was waiting to be tapped, but we didn't have the technology. Dozens of sweet spot Niobrara reservoirs have been identified. Boy, is that exciting. Lots of companies, lots of people made a lot of money on the Niobrara. Hundreds of millions of barrels of oil have been produced. More than 700 Niobrara abstracts, papers, theses, dissertations have been published. That's just done on a search of AAPG's data pages, and you get over 900 hits, but there's some repeats in that. And I started just estimating. That's a lot of work on the Niobrara. And finally, number 7, I think, is the most profound. It leads me right into my next slide. There have been new SEM studies and new logs that have provided new insights into the Niobrara depositional fabrics and pore types. And boy, do we understand that Niobrara reservoir now, thanks to all these things. So I'm going to dive right into one of those papers. This happens to be by Marshall Deacon and Bob Lieber with Noble, and they were doing scanning electron microscope work on the Wattenberg area. And I just love this slide. Since they published this slide in 2013, I've done quite a bit of SEM work on the Niobrara, and I can tell you that this slide just encapsulates the chalks beautifully. If you look at the left image, taken with secondary electrons, you've got pyrite framboids, the small round white blobs forming mostly in the marls, the darker areas. You've got these compacted lighter areas full of calcite, which are copepod fecal pellets. You've got some planktonic forams that are filled with equant sparry calcite over on the left side of the slide. And again, what happens here is you've got an abundance of copepod fecal pellets forming the carbonate component of the Niobrara. And when you zoom in on one of those pellets and look with a backscatter image on the right side, you can see all the coccolith debris. You can see the spines of coccoliths. It's just amazing. And I tried to give myself a visual estimate of how much porosity is in between that coccolith debris. It's almost all primary interparticle porosity and a scale of microns or less. And I'm estimating maybe 25% porosity within the pellet. It's much lower in the Marley matrix between the copepod fecal pellets. But this is amazing. And for a simple idea that just boggles the mind, if you want to quantify quality of reservoirs in the Niobrara, and you can quantify the amount of copepod fecal pellets, there's a direct correlation. The more carbonate material, coccolith debris, you have in the copepod pellets, the more porosity you have, the better storage for oil, and the better reservoir. It's such a simple concept, but I've never heard that expressed in words quite simply as that. So these SEM images really opened up my eye to a whole lot of new things. Even better was that we had new technologies, new techniques like X-ray fluorescence. And there was a student at School of Mines working with Steve Sonnenberg as part of the Niobrara Consortium that took the X-ray fluorescence gun and collected data down even closer than every half inch through a core from the Niobrara that was cut by Whiting Petroleum. It was called the Terrace core, 3632 core. And he put together a plot that represents 44 feet of this core, or 14 meters, because he put everything in meters, being a good graduate student. And you can see on the left-hand side the percent calcium carbonate, and he's colored the most carbonate-rich beds in a blue color, light blue, and the most carbonate-depleted beds, which are still running 50% carbonate, the marls, in grays and blacks, and so on. And this was published by Kasumi Nakamura and in 2015. And boy, I wish I could hear it, but there's a little black bed. I've got my cursor on it. I don't know if it's going to show up for you, but look at that black bed right in the middle of the beach, well, in the lower part of the beach chalk, but right in the middle of these cleanest chalks. And if you look, you see the calcium carbonate % drops, and then the calcium %, of course, drop. He's got low resolution data, high resolution data. And what is increasing in that little black bed is the silica and aluminum and vanadium. Vanadium can be a proxy for organic matter. And I'm going to tell you, I didn't know it back then. I didn't know it when he did his thesis. That's going to be a bed of keraginite of all things. And I'm going to show you that in the next slide too. So right in the middle of the beach chalk, we have these beds of keraginite. And if you can read the vanadium data, he's got lots of spikes rich in vanadium in the beach chalk itself, which is a little odd for a chalk-rich deposit. So poor old Nakamura hung up, as everybody else was in 2015, thought maybe I can relate all these chalk beds to cycles. And he went to Kaufman's work. Kaufman defined symmetrical cycles and asymmetrical cycles, so on and so on. And Nakamura put arrows on this. I'm not criticizing his work. He did what he could at the time. I think it's just wonderful. Look at that 3 set of arrows showing all the transgressions and regressions in the cycle model over on the left side of the diagram. He put a lot of thought into this, and he really liked transgressions and regressions like almost everybody else does. So I told you already about little keraginite beds. I didn't know these existed until just last fall when Steve Sonnenberg, thank you, Steve, had a core workshop as part of his Mudrock Consortium, Mudtalk Consortium. And the core is from the Razor Well, Whiting Core in northeastern Colorado in the Red Tail area. And I was just amazed. You looked at that core in detail and you could see right in the B chalk, and I've got a couple double-headed arrows pointing at normal B chalk reservoir facies. You had these black beds that are very thin, mostly less than a centimeter, the scale bar in here are centimeters. And you got a thick one down in the lower left that's at least, what, 2 or 3 centimeters thick, over 1 inch thick. And then you've got others that are just a couple millimeters thick, and some of these are a centimeter thick. We actually have in the Niobrara keraginite beds with 20 weight % TOC, 40% by volume, plus or minus. And this is amazing. Whiting, with their team of geologists, Lynn Cantor and Mark Sonnenfeld and others, recognized these a number of years ago. But Whiting didn't want to release this data. They didn't want people knowing that there were some really good organic rich source rocks. And to the team, to the credit of the Whiting team, they kept this information secret all that time. But this is amazing. We've got some really organic rich beds right within the beach chalk. And the question is, what is their depositional environment? How did these things form? You're not going to do it with sea level fluctuations, I don't think, because the high stand chalks are suddenly, instantly going to go to low stand keraginite beds. It's an option, not one I happen to believe. Even more striking to me is I went to a talk in 2017 by Steve Camilla. Steve's been a friend of mine for more than 20 years. And he flashed some slides up using color-filled gamma ray technology. He uses Petra, and he can color-fill the gamma ray such that really clean, low gamma ray rocks in the Niobrara show up in shades of blue, and real shaly or marly rocks with high gamma ray show up in shades of gray, almost to black. And he put a section together that's roughly 30 miles long across parts of Wattenberg Field. And I looked at this just to get you oriented. Sharon Springs is at the top. It's nearly black because, you know, it's very carbonate poor, very hot gamma ray, full of organic matter. Fort Hayes limestone's at the bottom of the diagram. Very clean, cleanest limestone around, nice blanket. And in between, you have all these lenses of B chalk thickening and thinning, C chalk thickening and thinning, even A chalk almost pinching out across Wattenberg Field. And I looked at this and I thought back to our depositional model of blanket-like deposition during the Niobrara with the chalks that we could correlate for 100 miles. And I said, what's wrong? Steve, what's going on? I didn't actually say it, I thought it. But it brought back memories of how Susan and Barbara and I struggled with the C chalk and the B chalk to a lesser extent, thickening and thinning over short distances, just a few kilometers. And I can remember very well one morning when Susan came into the project we were doing and big smile on her face, said, I was reading some German literature last night, and they have a word for these thicks and thins that are chalk, and they call them Peilenpuppen. And Peilen is just basically a pile of poop, because that's where the copepod fecal pellets are. And so we adapted the term, actually published it in our 1998 paper. I did a search on Peilenpuppen on AAPG. The word has been used only one time in the last 20 years by Steve Sonnenberg in a paper on the Wattenberg field, and he mentioned the presence of Peilenpuppen chalk deposits in Wattenberg. And I thought, oh, at least somebody's heard of them. And that's how we, at the time, explained this. And Steve had a second cross-section. I should mention these tops are based on Orion Skinner's work. They worked together at Whiting, Steve and Orion. And here's a different cross-section. You can see how the A chalk is disappearing. That's why the ages on the core that I showed you are so confusing. And look at the reciprocal deposition. You get a thick in the C chalk, and then the thick B marl, and then the B chalk. And so a lot of things are going on. And I thought to myself, Steve, this is just this boggles my mind. What's it mean? And even better, I saw a second paper by Marshall Deacon, Katie Joe McDonough in 2018 in the Salt Lake City ACE convention. And they showed the same thing, 100 miles, Township 1 south to 16 north, along the western side of the Denver Basin, and they show the same reciprocal deposition. So again, my mind was boggled. The same year, a paper came out in 2018. Well, these are my ideas. The cross-section suggests that Niobrara deposition was not blanket-like at all and not sea level driven. What's going on? Let's look at a possible modern analog. It's on the opposite side of the globe off New Zealand's South Island. And this is a paper by Jess Hillman and 3 or 4 other people published in New Zealand Journal of Geology and Geophysics. If you're oriented, you'll get to recognize the South Island is in a shade of gray with the cities of Christchurch and Dunedin in the Southern Alps over on the upper left side. And they've color-coded water temperatures in shades of green being cool and warm being red. And these are water temperatures at a depth of about 100 meters. And I'm going to specifically suggest you take a look at that area labeled number 2, the box number 2 on the right center side of the slide. And you'll see that it sits at water depths, if you could read the numbers, and I can, at water depths of 500 to 900 meters. And I'm going to look at some, in the next slide, at some depositional features. But what Jess Hillman and her co-authors concluded in their very first sentence of their abstract is up there on the top of the slide in yellow. Submarine currents are a principal factor in controlling seafloor geomorphology. If I wanted to be an author and write a short, succinct sentence that captures what's going on in deep water, I could not do any better than Jess Hillman did with that sentence. Submarine currents, who would have thought at depths of 500 to 900 meters could be shaping the seafloor? And what's happening here is we have an interaction of subtropical warm currents, which are in red, STW up at the top of the slide, interacting with the SAW, subantarctic cool nutrient-rich waters in green. And what these currents do when they interact is shown in this slide, a seismic profile across that area showing scours up to 100, even 150 meters deep in these soft calcareous hemipelagic oozes. And then you get on the lee side, the point bar, if I can use that term for something in 500 meters of water, drift sediments that have the same pinch and swell structures that we saw in the Niobrara. And I thought, my goodness, I've got an analog. It happens that this area of New Zealand is at 44 degrees south latitude. At Cretaceous time, Colorado was at 50 degrees north latitude. So even our latitudes where you could be interacting cooler waters and warmer currents to form these sorts of drift sediments was similar, but 80 million years apart and half a world apart. And there are lots of other examples when you start looking. I just pulled a slide that was published way back in 1993. I was completely unaware of this paper. Looking between Sicily and Tunisia, you've got the Sicily Channel, you've got currents flowing through there, Mediterranean currents, creating all sorts of fill in a very deep fault-bounded graben. And so my whole point here, a similar interplay of cool Arctic currents and warm Gulfian currents in the Western Interior Seaway could explain the distribution of chalks versus marls in the Niobrara better than transgressive regressive sea level changes. This deep marine current hypothesis also explains the Niobrara scour and drift features in the Denver Basin, shown on Camilla and Marshall's cross sections. And finally, I think it helps explain and helps me understand the pile-and-poop-in deposits of the B and C chalks. So my conclusion is what everyone knew in 1998 was wrong. The Niobrara is a deep water deposit, that part's true, but deep water environments are not quiet and boring. Deposition is not slow or passive, but dynamic. Siliciclastic sediment transport in the Western Interior Seaway was not downwardly easterly from the severe highlands, but southerly along the basin axis. All those clays are coming in with those Arctic currents along with the organic matter. Chalk benches are not formed from a gravity-driven rain of pelagic debris, but they're current traction deposits on the seafloor. They're carried and there's erosion and scour and deposition all going on in 100 meters of water or more. And once the chalk and marl sediments are on the seafloor, they can be extensively reworked by marine currents. So my ideas have changed 180 degrees on what was going on in Niobrara during that time. Some parts of this talk were recently published in the April 2020 issue of the Mountain Geologist, available on RMAG's website for members. And I would invite people, if you have the time and interest and stimulated thoughts or questions that we don't get answered in the next 10 minutes or so, you could email me, mwlongman1@gmail.com. I'd be happy to correspond or reach out to anyone that's wanting to share thoughts. And finally, I'd really like to thank the RMAG staff and John Ladd for giving us the opportunity to present this talk. When this was originally proposed back in December of last year, it was going to be a lunch talk at Maggiano's. Clearly that couldn't happen, but this is a good alternative. I can share ideas with everybody online, I hope, and stimulate some thought. I've had a lot of discussions with a lot of people. They're listed here: Gus Gustafson, Steve Camilla, Lynn Cantor. I can't read them all, but anyway, thanks to everyone that's helped share this. But any errors are my fault. I take responsibility. I don't promise I've done everything right. We hope this talk has offered some new insights into Niobrara deposition, and thank you for listening.